Have you ever actually stopped for a second and thought about the literal copper wire powering the device you're listening on right now?
Most people definitely haven't.
Right. I mean, we just expect it to be there. We expect it to conduct electricity, to carry our data, to basically make every single aspect of our modern world possible. But that incredibly thin, highly refined piece of metal inside your headphones or running through the walls of your house likely has an origin story that goes back 100 million years.
At least 100 million years, yeah.
Yeah, and we're talking about an epic saga here. It involves violent tectonic plates crashing into each other, ancient underwater volcanoes spewing this black metallic smoke into prehistoric oceans, and a massive slow-motion chemical refining process that was engineered by the Earth itself. It's a journey from the fiery, crushing depths of the planet directly to your ears.
It really is one of the most profound stories of deep time that we interact with every single day. We look at a spool of copper wire or a circuit board, and we just see infrastructure, we see human engineering. But what we're actually looking at is the final polished product of planetary scale forces. We're looking at forces that concentrate these valuable trace metals, forces that hide them miles underground, shift them around over eons, and eventually—
By geological accident.
Exactly, almost by geological accident, reveal them.
And they're revealed either through millions of years of natural relentless erosion or through modern human mining.
Right, precisely.
Okay, let's unpack this. Today, our mission on this deep dive is to explore the staggering reality of how this actually happens.
It's a complex process.
It really is. So we're basing our conversation around the data and insights from two incredibly detailed, monumental geological reports. The first is a sweeping, comprehensive history of southwestern North America put together by Porter Geoconsultancy.
An incredible resource.
It really is. It looks at the massive tectonic evolution of the region and something called supergene enrichment, which is essentially nature's own chemical solvent extraction plant.
Oh.
And then the second piece of our puzzle comes from the USGS, looking at volcanic-associated massive sulfide deposits, or VMS deposits, and the intense environmental signatures they leave behind.
Which is the totally other side of the coin.
Right, exactly.
Yeah.
So we're going to trace this journey from how the Earth manufactures these massive metal vaults, how it chemically upgrades them, to what happens when those ancient vaults are finally cracked open and exposed to our modern atmosphere.
And honestly, looking at these two sets of data together is the perfect pairing.
How so?
Well, the Porter research gives us the deep tectonic and chemical history. It answers the how did it get there and why is it so incredibly concentrated part of the equation. It's the grand architecture of the geology.
Okay.
Then the USGS data brings us crashing back into the present day. It shows us that the exact same intense chemical processes that enrich the copper over tens of millions of years are still highly active today.
It's happening a lot faster.
Precisely. And when those rocks interact with our modern atmosphere and our water cycles at an accelerated rate, they present some of the most significant environmental challenges on the planet.
So, to understand the wire in your wall, we have to start at the absolute beginning. In the Earth's natural forges, we're looking at two very distinct types of copper deposits here.
Yes.
First, we have the porphyry copper deposits, and second, we have the volcanic-associated massive sulfide deposits, which geologists usually just call VMS deposits. Let's tackle those massive porphyry deposits first.
Good place to start.
Because when you look at the research focusing on the southwestern United States and northern Mexico, the scale is just hard to wrap your head around. There are over 50 significant deposits spanning a 2,000-kilometer belt stretching across that landscape.
It is undeniably one of the most important and prolific copper provinces on the entire planet. And to understand why it's there, you have to look at the massive tectonic setting. These porphyry deposits formed in what geologists call a continental margin cratonic setting, directly above a major subduction zone.
Let me just jump in and translate that a bit, because continental margin cratonic setting sounds like a mouthful.
It is a bit jargon-heavy, yeah.
Essentially, a craton is the old, thick, stable heart of a continent. So we are talking about the thick edge of the North American tectonic plate. And right off the coast, you had the ancient Farallon Oceanic Plate, which was dense and heavy, physically diving beneath the lighter North American continental plate. That's your subduction zone.
Precisely. You have this massive conveyor belt of oceanic crust diving down into the mantle. And this process was active for a very long time, from the early Mesozoic well into the late Tertiary period.
Wow.
But the absolute peak of this activity, the golden era for manufacturing these specific copper deposits in the Southwest, happened during a specific window that geologists call the Laramide Arc.
The Laramide Arc.
Yes.
That ran roughly from 80 million to 50 million years ago, right?
Correct.
With a real peak of intense activity between 72 and 55 million years ago.
That's the exact window. This was an era of profound, intense magmatism and crustal shortening.
Crustal shortening meaning the plates are pushing together so hard the land is physically squishing and folding.
Yes, exactly. You have to picture what's happening deep underground. As that oceanic plate dives deeper, the incredible pressure and heat cause it to release water and other volatiles.
Okay.
This water lowers the melting point of the surrounding mantle rock above it, creating immense bodies of magma.
Because wet rock melts at a lower temperature than dry rock.
Right, just like adding salt to ice changes its melting point. Because this magma is hot and buoyant, it begins to rise, pushing its way up into the thick continental crust.
Like massive, molten hot air balloons trying to float to the surface.
Exactly like that. And as these giant magma chambers slowly cool and crystallize miles beneath the surface, they go through a process of fractional crystallization.
What does that mean exactly?
Well, water, sulfur, and incompatible metals like copper and gold don't fit easily into the crystal structures of the first minerals that form.
Oh, so they get left out.
Right, so they get concentrated into the remaining liquid. Eventually, the pressure of this superheated, metal-rich, aqueous fluid becomes so immense that it literally shatters the surrounding solid rock.
Whoa.
It hydraulically fractures the crust over cubic miles.
That is such a violent image. Just cubic miles of solid rock exploding outward from internal pressure.
It is violently explosive on a microscopic, pervasive scale. And those superheated fluids rush into all those millions of tiny new fractures.
And then what?
As the fluid cools, the metals precipitate out, creating vast, sprawling networks of microscopic veins filled with copper, iron, and sulfur minerals.
And that's the deposit.
That is your classic porphyry system.
Yeah.
It's an unfathomably huge volume of rock, but the copper is spread out in these tiny veins, meaning it's generally a very low-grade deposit.
So that entire massive explosive process is happening miles deep underground on the coast. Now, let's contrast that with the VMS deposits, because they sound entirely different. They're described as lens-shaped to sheet-like bodies associated with submarine volcanoes.
What's fascinating here is the contrast in environment. While those massive porphyry deposits are forming deep in the roots of the volcanic plumbing system, VMS deposits are forming right at the surface but underwater.
Ah.
They are the ancient equivalents of the black smokers that marine biologists and geologists study at the bottom of the ocean today.
I love that image. If you were standing on a Jurassic or Cretaceous coastline millions of years ago, you'd have these violent subduction zones churning out massive magma bodies deep beneath your feet, cooking up those porphyries.
Right.
But if you looked offshore, down at the bottom of the ocean, you'd have these deep underwater hydrothermal vents spewing jet black, 400-degree metal-rich smoke into the freezing seawater.
And when that superheated fluid hits the cold ocean, the metals instantly precipitate out and pile up on the seafloor to form these massive VMS mounds.
It's a spectacular visual.
It is. And when you find a VMS deposit outcropping on dry land today, you are essentially walking around on a preserved, ancient seafloor.
That's wild.
You can even see what geologists call stringer zones directly beneath the massive sulfide mounds.
What are stringer zones?
They're networks of quartz and sulfide veins rooted in the rock below, and they represent the actual fossilized plumbing system, the hydrothermal pipes that fed those very vents on the seafloor.
It's literally the throat of the volcano preserved in stone.
Exactly.
And the research breaks these VMS deposits down into three main types based on where and how they form.
Yes.
I'll take a crack at the first one, the Cyprus type. These are, as you'd guess, named after the famous deposits in Cyprus, like the Sciritissamine.
Right.
These tend to be smaller, medium grade, and very rich in copper and zinc. And the key here is that you find them in what are called ophiolite sequences.
Yes, ophiolites are crucial here.
Now, just to paint a picture for everyone, an ophiolite isn't just a type of rock. It's actually a massive, displaced chunk of the actual ocean floor, specifically extrusive basalts that got caught in a tectonic traffic jam and was physically shoved up onto dry land.
That's a perfect way to describe an ophiolite. It's oceanic crust that has been abducted or pushed up rather than subducted down. So Cyprus types are pure deep ocean volcanic systems.
Okay, what's the second type?
The second type of VMS is the Kuroko type. These are named after the massive deposits in the Kuroko district of Japan, although the Kidd Creek deposit in Ontario is another world-class example.
And they form differently.
Very differently. They form in extensional environments associated with arc volcanism.
So instead of the deep ocean floor, this is more like a volcanic island chain tearing itself apart.
Exactly. And because of that setting, they form in intermediate to felsic volcanic rocks like rhyolite, rather than the basalt of the ocean floor.
Does the rock type matter that much?
That difference in host rock chemistry is absolutely crucial. Kuroko types are high-grade and can grow to be very large. They are also incredibly rich in a wider suite of metals, zinc, lead, silver, and antimony, along with the copper.
Oh, wow. So a lot more variety.
And what's really unique about them is that they exhibit strong geochemical zonation.
Zonation meaning the metals sort themselves out into distinct layers as they pile up around the vent.
Right, because different metals precipitate at different temperatures as the hydrothermal fluid mixes with the seawater. They separate into distinct zones.
How does that look in the rock?
You typically find a hot, copper-rich core right at the throat of the vent, and as you move outward to cooler zones, it grades into zinc, and then out to lead and silver on the fringes.
That brings us to the third type, the Besshi type. These feel like a bit of a hybrid. They form in mixed volcanic sedimentary environments.
Yes.
The research describes them forming alongside turbidites. For anyone who isn't a deep-sea oceanographer, a turbidite is essentially a massive, violent, underwater avalanche of sand and mud rushing down the continental slope.
So imagine these massive sediment avalanches constantly burying the seafloor.
Okay.
And into that thick pile of wet sediment, basaltic magma injects itself as sills. A great example of this is the massive, windy, craggy deposit up in British Columbia.
Do they look different from the other two?
Completely. Because they're forming in and around these soft, flat, sedimentary layers, Besshi deposits don't form the steep mounds like the other two. Instead, they form thin, laterally extensive sheets of massive sulfide rock, stretching out over huge areas.
And what kind of metals are in there?
They're very rich in copper and pyrrhotite, which is a magnetic iron sulfide.
It's amazing how much variety there is in the final metal deposit, just based on what kind of rock the volcano's erupting through and whether it's erupting onto bare rock or a pile of mud.
The environment controls everything.
It really does. But let's pivot back to those massive, low-grade porphyry deposits in the southwest. The research makes a really crucial point. Even though these laramide arc deposits are mind-bogglingly huge in terms of volume, many of them wouldn't be economically viable at all without a secondary process.
They would just be interesting rocks.
Right. Nature had to step in and upgrade them through a process called supergene enrichment. Here's where it gets really interesting. Nature basically built a millions of years long chemical refinery to turn low-grade rock into high-grade ore. How exactly does this solvent extraction plant work?
This is truly one of the most elegant, powerful chemical processes in all of geology. Supergene enrichment is, at its core, a form of extreme, prolonged chemical weathering.
Okay.
Remember, those porphyry deposits formed miles underground. You start with this primary, or hypogene ore. This primary ore contains simple sulfide minerals like pyrite, which most people know as fool's gold, along with chalcopyrite and bornite, which contain the copper.
So they're just sitting down there.
Yes, but geology is never static. Over millions of years, tectonic uplift pushes these rocks upward, and physical erosion strips away the miles of rock above them.
So it unburies them.
Eventually, this primary ore is brought right up to the surface, where it is suddenly, for the first time in its existence, exposed to atmospheric oxygen and rainwater.
And that exposure is the trigger.
Yes.
The moment oxygen and water hit that deep earth rock, the chemistry kicks into high gear. And the star of the show here, the absolute crucial engine driving this whole refinery, is pyrite.
Absolutely.
Why is fool's gold the most important piece of the copper puzzle?
Because pyrite is highly unstable in the presence of oxygen and water.
What happens to it?
When pyrite oxidizes, it undergoes a complex chemical reaction that produces two incredibly aggressive byproducts, sulfuric acid and the ferric ion.
Wow.
So just by raining on this rock, nature creates a highly acidic, low pH solution, a literal acid wash, that begins trickling down through the fractures.
And that acid attacks the copper.
This acid is so strong that it literally dissolves the primary copper minerals sitting near the surface. The copper goes into solution, and it's stripped completely out of the upper layers of rock.
Leaving what behind?
What's left behind at the surface is a barren, crumbly, red and yellow, iron-stained zone that geologists call the leached capping.
Okay, so I always like to think of this using a coffee analogy to make it stick. Imagine you are making a strong pour-over coffee. The rainwater falling on the mountain is the hot water. The pyrite in the rock acts as the coffee grounds, releasing the acid that extracts the flavor, which in this geological case is the copper.
That's a great way to visualize it.
So the acid washes through the rock, dissolving the copper, carrying it downward in a liquid state. But where does it go? It doesn't just keep falling toward the center of the earth.
No, it follows gravity down through the microscopic fractures in the rock until it hits a very specific barrier, the water table.
The water table.
And the water table represents a stark, fundamental chemical boundary. Above the water table, the environment is full of air. It is oxygen-rich, or what we call an oxidizing environment.
Okay.
But below the water table, all the pore spaces in the rock are completely filled with water. There is no free oxygen. It is a reducing environment.
So the chemistry changes.
When this highly acidic, dissolved, copper-rich liquid hits this reducing environment at the water table, the chemistry abruptly and violently shifts. The dissolved copper can no longer stay in solution.
What happens to it?
It drops out and it precipitates directly onto the unoxidized solid primary sulfides that are just sitting there below the waterline.
It essentially electroplates itself onto the existing rocks. It coats them in pure copper goodness.
Exactly like electroplating. The copper in solution chemically reacts with the primary minerals and transforms them into much richer secondary copper sulfide minerals, predominantly a dark, sooty mineral called chalcocite.
Chalcocite.
Okay. Now, because the water table is generally a flat, horizontal plane beneath the ground, this precipitation process creates a highly concentrated horizontal layer of ore known as an enrichment blanket.
Ah, so this is the cup in your coffee analogy where all the good extracted stuff pools and concentrates.
Precisely. And this process, running continuously over millions of years, can upgrade the copper concentration to 2, 5, even 10 times its original primary grade.
10 times.
It literally turns a massive mountain of uneconomic, worthless rock into a world-class, multi-billion-dollar resource.
It's just staggering to think about the timescale required for water dripping through rock to move millions of tons of copper.
It requires immense patience from the earth.
But it's not a guarantee, right?
Yeah.
You can't just take any copper deposit, leave it in the rain for a million years, and expect an enrichment blanket. The research emphasizes that this requires a perfect, precise Goldilocks environment.
If we connect this to the bigger picture, it is an incredibly delicate balancing act of 3 major factors: climate, tectonic uplift, and the specific chemistry of the host rock itself.
Let's break those down. Let's look at uplift first.
You need the tectonic plates to be pushing the land upward to create a hydrological gradient. Basically, you need a slope. The water needs a reason to flow downward through the rock.
Makes sense.
But if the tectonic uplift is too aggressive and the mountains are rising and eroding too fast, the physical erosion, the landslides and the rivers, will physically strip away the rock faster than the slow chemical weathering can do its job.
So the whole copper system just gets physically washed down the river into the ocean.
Exactly. So the uplift has to be slow and steady.
And climate is the second variable. You can't have this happen in a frozen tundra or a lush rainforest.
Right. You need a specific climate to drive the oxidation and evaporation cycle. The ideal setting is a hot or temperate semi-arid climate.
Like Arizona.
Very much like Arizona. You need distinct wet seasons to provide the rain to flush the system, followed by long, hot, dry seasons to allow oxygen to penetrate deeply into the lowered water table and drive the oxidation of the pyrite.
Which brings us to the third Goldilocks factor, and this one blew my mind: the chemistry of the surrounding rock. It turns out the rock holding the copper can actually sabotage the entire refinery process.
Crucially so. Let's say your copper deposit was injected into a massive layer of limestone, which is a carbonate rock.
Okay, limestone.
Limestone is basically calcium carbonate. If you've ever taken a Tums for heartburn, you know what carbonates do.
They neutralize acid.
They act like a giant geological antacid tablet. As soon as the oxidizing pyrite produces that sulfuric acid, the limestone host rock instantly neutralizes it. It buffers the acid, raises the pH back to neutral, and the whole solvent extraction process shuts down.
The acid loses its bite and the copper just gets stuck.
Exactly. The copper immediately precipitates right where it is, near the surface, forming beautiful but highly disposed green and blue oxide minerals like malachite or azurite.
So you don't get a blanket.
You do not get that deep downward migration necessary to form a massive concentrated chalcocite blanket at the water table.
So what kind of rock do you need?
For a thick, rich sulfide blanket to form, you need host rocks that are relatively inert, rocks that won't fight the acid. Potassium aluminum silicates, for example, are perfect. They let the acid stay strong, allowing it to act as a powerful conveyor belt, carrying the copper hundreds of meters all the way down to the water table.
That is just wild. The Earth is literally running a giant, finely tuned chemical plant, complete with its own acid supply and precipitation tanks.
It really is.
And one of the most amazing things about the Porter data is that geologists have actually figured out exactly when this chemical plant was operating. They can date a weathering process.
Yes.
Which sounds impossible. I mean, you can't just carbon date a rock from 50 million years ago, especially just a weathered rock.
No, carbon dating is completely useless here. It only works for relatively recent organic material, maybe up to 50,000 years old. Here, to peer millions of years into the past, geochronologists rely on potassium-argon, or Kr, radiometric dating.
How does that work on weathering?
It works beautifully because of the specific chemistry of the weathering. When that intense acid weathering occurs in the leached capping, it destroys the original minerals, but it also creates entirely new secondary minerals in their place.
Like what?
Specifically sulfate and clay minerals like jarosite, alunite, and elite.
And the key is that these new minerals suck up potassium when they form, right?
Yeah, exactly. They incorporate naturally occurring potassium into their brand new crystal structure as they're being born in the acid wash. And a very tiny fraction of all potassium in nature is a radioactive isotope, potassium-40.
Okay.
Over millions of years, this radioactive potassium decays at a very precise known rate into argon gas.
And argon is a noble gas.
Right, because argon is a noble gas, it doesn't chemically bond with anything, it just gets physically trapped, locked inside the microscopic cage of the mineral's crystal lattice.
So the mineral acts like a tiny geological hourglass.
That's a perfect analogy. By taking a sample of that jarosite and using a mass spectrometer to measure the exact ratio of the remaining parent potassium to the trapped daughter argon gas, we can calculate precisely when that specific mineral crystal formed.
We can tell exactly when the acid was flowing.
Exactly.
And what's even cooler is that there's a specific sequence to these minerals. They don't all form at once. The presence of jarosite versus alunite tells a whole story about the pH of the water at that exact moment.
Yes, the mineralogy is a direct recording of the changing chemistry over time. Based on thermodynamic chemical modeling, we know that jarosite forms when the primary sulfides are actively, aggressively dissolving.
So lots of acid.
The pyrite is burning,
Right.
and the pH is incredibly low, highly acidic. It's a harsh environment. But eventually, after maybe hundreds of thousands of years, all the primary sulfides in that upper zone are completely dissolved and exhausted.
The fuel for the acid fire runs out.
And when the acid production stops, the pH begins to creep back up toward neutral.
The environment becomes slightly less acidic.
Precisely. And in that new, higher pH environment, jarosite is no longer stable, but alunite is. So alunite starts to precipitate instead.
Okay, so if a geologist finds both.
Therefore, if a geochronologist looks at a thin section of rock under a microscope and finds alunite crystals physically cutting across and replacing older jarosite crystals, it tells them a clear story.
Which is?
They're looking at a rock that experienced the harsh early stages of acid weathering and then survived into the final dying stages of a complete weathering cycle.
Which is the perfect transition to the next huge piece of this puzzle. Because we've established that to build this beautiful, thick enrichment blanket, you need a stable water table.
Yes, stability is key.
The copper needs a specific horizon to pool against, but the tectonic history of the American Southwest is the exact opposite of stable.
It really is.
It's a chaotic, violent timeline of mountains rising, valleys collapsing, and entire landscapes tilting on their side.
It is an incredibly dynamic, almost violent geological history. Let's trace the major eras as outlined in the detailed structural data.
Let's do it.
We talked earlier about the Laramide Arc, the period of huge magma chambers and explosive fracturing, ending around 50 million years ago. What followed that was a long 15 million year period of relative calm called the Eocene epeirogeny, stretching from roughly 50 to 35 million years ago.
Epeirogeny basically means broad, slow uplift of a continent, right?
Yeah.
Without the intense folding or faulting.
Exactly. It was a time of magmatic quiescence, the volcanoes had shut off, but the entire region was slowly being pushed upward, which drove massive landscape-scale erosion.
So it's scraping off the top layers.
This is the crucial era when the tops of those old laramide volcanoes were completely chewed away by wind and rain, finally exposing the deep, copper-rich porphyry roots to the atmosphere.
And kicking off the refinery.
This Eocene period kicked off the very first massive wave of supergene enrichment across the entire Southwest.
So you have 15 million years of this slow, steady chemical refinery building up these great copper blankets. But then around 35 million years ago, the tectonic plates shift and all hell breaks loose again. We enter the mid-tertiary orogeny.
Right. From 35 to 18 million years ago, the landscape is transformed. First, we see renewed voluminous volcanism.
But not just regular volcanism.
But this isn't just lava gently flowing from a crater. We are talking about colossal caldera-forming eruptions that send out hurricane-force avalanches of superheated gas, ash, and pumice called ignimbrites.
Wow.
These incandescent ash flows swept across the landscape, filling in valleys and instantly burying the old eroded surfaces and the copper blankets under thousands of feet of solid volcanic rock.
But the ignimbrites weren't even the most disruptive part. The research points out that this was a time of massive crustal extension. The North American plate literally began to stretch apart.
This is where it gets highly structural. Imagine the crust of the Earth behaving a bit like warm taffy over millions of years. As the tectonic forces pulled the Southwest apart, the crust thinned and fractured.
And that causes faults.
This stretching created a specific type of structural failure known as listric faults.
Let's define listric faults, because this is wild. If a normal fault is just a straight diagonal crack where one block slides down, a listric fault is curved, right? Like the shape of a spoon.
That is the exact geometry. The fault plane is steep near the surface but curves to become almost flat at depth.
Okay, so what happens when it moves?
Because it's curved, when a massive block of the Earth's crust slides down that fault, it doesn't just drop straight down, it rotates, it tilts backward as it slides down the curve of the spoon.
It tilts the whole block.
And this massive block rotation tilted entire mountain ranges, including the copper deposits locked inside them. The geological data shows that some of these massive deposits were rotated and tilted up to 60 degrees.
Imagine a completely flat, horizontal copper enrichment blanket. A blanket that took 15 million years to form perfectly level with the water table, suddenly being tipped up like a massive skateboard ramp.
It's hard to visualize on that scale.
It is, and it doesn't stop there. From 18 million years ago to the present day, the tectonic shift yet again, and we enter the Basin and Range era.
The Basin and Range is the landscape we see today if you fly over Nevada or southern Arizona, that endless washboard terrain of alternating mountains and valleys.
What's happening structurally there?
This era is characterized by block faulting. The crust was no longer stretching and rotating as much. Instead, it was breaking into massive, parallel vertical blocks.
That's straight up and down.
Some blocks dropped straight down to form incredibly deep valleys, which we call gradins, and the adjacent blocks were pushed straight up to form linear mountain ranges.
How big of a drop are we talking?
The structural relief, the vertical distance between the bedrock floor of those downdropped basins and the jagged peaks of the ranges, can be 2 to 4 kilometers. In some extreme cases, it's up to 6 kilometers of vertical displacement.
So if you're the copper deposit, you've been cooked in a volcano, exposed, weathered, buried in ash, tilted on a curved fault, and now you're either being thrust 3 miles into the sky or dropped 3 miles into a dark valley.
Quite the journey.
How does this chaotic roller coaster actually impact that delicate copper refinement process? It seems like it would just destroy it.
It definitely disrupts it, but paradoxically, it often makes it significantly better.
How is that possible?
This tectonic chaos creates multiple overlapping pulses of supergene enrichment. Think about it. As these faults move and mountains rise during the Basin and Range era, an old, flat enrichment blanket that formed millions of years ago might be suddenly lifted high above the new modern water table.
Suddenly it's stranded high and dry.
Exactly. It is no longer sitting safely in that anoxic, reducing environment below the waterline. It's suddenly pushed up into the vadose zone, exposed to oxygen all over again.
So the refinery restarts.
The residual pyrite left in the rock wakes up. It starts generating fresh sulfuric acid, and incredibly, it begins to dissolve the already enriched chalcocite blanket.
It dissolves its own enrichment.
The copper is leached out a second time, travels downward through the rock again, and forms an even richer, vastly more mature supergene blanket at the new, lower water table.
Wow.
Every single tectonic pulse, every time the Earth heaves and shifts the water table, acts like another cycle in a massive chemical distillation column, refining and upgrading the ore further and further.
The case studies and the geological data really bring this chaotic history to life. Let's talk about Ajo, Arizona, because the geology here sounds completely unhinged.
Ajo is the absolute textbook example of severe tectonic disruption and listric faulting.
What happened there?
Originally, back in the Eocene, the chalcocite enrichment blanket at Ajo formed perfectly horizontally at the water table, just like it's supposed to. It was a classic, flat, tabular body of ore.
But then it stretched.
But during that intense mid-tertiary extension, the listric faulting in that specific area was so severe that the entire deposit, the whole mountain, was rotated. The data suggests it was tilted at least 60 degrees and possibly up to a staggering 120 degrees.
Wait, 120 degrees? That means it wasn't just pushed on its side, it was pushed past vertical. It was slightly upside down.
Exactly. A horizontal blanket was flipped on its head, and then, while it was sitting there violently tilted, the landscape above it was actively eroding.
And it got buried.
A massive, catastrophic alluvial fan deposit, basically a mountain-sized debris flow of boulders and gravel known as the locomotive fanglomerate, came crashing down and dumped over the top of the eroded surface, completely burying the tilted blanket.
So, millions of years later, when geologists and miners finally discovered and exposed the Ajo deposit, they didn't find a flat blanket.
No, they found a tabular body of incredibly rich or plunging steeply, almost vertically into the earth, running perfectly parallel to the contact line with the overlying locomotive fanglomerate.
It's like finding a buried, tilted skyscraper made of pure copper. It completely defies the standard model until you understand the tectonic history.
Exactly, you have to know the history.
And then you have the deposits at Secatin and Santa Cruz, also in Arizona. These are incredible because they were completely hidden from the surface.
Yes, the basin and range faulting hid them perfectly. Secatin and Santa Cruz are located in blocks that drop down during that faulting.
Deep down.
They were buried under a massive graben that slowly filled with up to 1,100 meters of gravel and sediment washed down from the adjacent mountains. They were completely invisible from the surface.
But structurally, what makes Santa Cruz so fascinating is the phenomenon of exotic deposits.
Yes.
I love this concept. How does an exotic deposit form?
At Santa Cruz, tectonic activity had faulted a block of highly permeable but completely unmineralized mid-tertiary volcanic rock right up against the older, copper-rich porphyry deposit.
So a barren rock next to a rich rock.
Now remember that acidic, copper-laden water migrating downward. As those supergene solutions moved through the fractured system, they hit a barrier and didn't just go straight down.
Where did they go?
They actually migrated sideways, flowing laterally out of the source porphyry and into the barren neighboring volcanic rock.
Okay.
As the fluid reacted with the volcanics and the pH rose, the copper precipitated there as striking green and blue oxide minerals, atacamite and chrysocolla.
So it essentially leaks sideways and painted the neighboring rocks with copper.
Precisely. It created a totally separate, exotic copper deposit in rocks that originally had absolutely no copper in them whatsoever. The copper traveled to a new zip code.
That is amazing. Then there's the San Manuel and Kalamazoo story. I love this one because it literally sounds like a massive geological magic trick. A sawing a lady-in-half illusion, but with a mountain.
It is an incredible piece of geological detective work that took years to figure out.
So what's the trick?
Originally, San Manuel and Kalamazoo were not two deposits. They were a single, continuous, roughly cylindrical porphyry ore body that formed vertically in the crust.
One big cylinder.
But during the intense mid-tertiary extension, a massive low-angle extensional structure called the San Manuel Fault developed. And this fault physically cut right through the dead center of the deposit on a diagonal.
Oh, wow.
As the crust stretched and pulled apart, the top half of the ore body, which we now call Kalamazoo, was sheared off and physically slid away in the hanging wall of the fault, sliding down the structural ramp.
Leaving the bottom behind.
The bottom half, San Manuel, remained behind, anchored in the footwall.
So the fault literally sliced a multi-million-ton mountain of solid rock in half and moved the top piece down the road. That is almost impossible to picture.
The sheer physics of it are astounding. And the
Hmm.
most interesting consequence of this separation is that because they were moved to different structural elevations, they experienced entirely different supergene weathering histories for millions of years.
Because one was high and one was low?
San Manuel, remaining in the Footwall block, was repeatedly exposed to the atmosphere. It underwent multiple distinct stages of profound weathering and enrichment, perfectly matching the well-documented erosional cycles of the local Cenozoic rock formations. It was heavily oxidized and enriched.
But Kalamazoo, the top half that slid away, had a totally different fate.
Right, Kalamazoo, sitting in the hanging wall, ended up being downdropped and largely buried, protected from the elements.
So it missed out on the enrichment.
It only possesses a very thin, early, immature chalcocite blanket that formed before the faulting. And just like Ajo, that blanket was tilted to an almost vertical orientation as the block rotated, with very little subsequent oxidation after it was buried.
So you have two halves of the exact same original ore body, born at the exact same time, but because of one fault, they were weathered and altered entirely differently.
It's a perfect natural laboratory.
Let's move further south to Bisbee, Arizona. The data points out that this is one of the oldest major deposits in the region, dating all the way back to the Jurassic period, roughly 178 to 163 million years ago.
Very old.
Now, logically, because it's so incredibly old, it has the longest potential history of weathering.
Bisbee is remarkable primarily for its deep preservation. The primary porphyry and the massive carbonate replacement ores formed way back in the Jurassic. Following their formation, they were exposed to a massive, prolonged period of supergene oxidation and enrichment.
How deep did it go?
Because the host rocks were heavily fractured, the oxidation reached an astounding 500 meters deep into the bedrock. We're talking about half a kilometer of solid rock oxidized by rainwater.
But wait, if it's 170 million years old, how did that oxidized zone survive the millions of years of subsequent erosion? Shouldn't it have been washed away during the Eocene?
That is the stroke of geological luck at Bisbee. In the early Cretaceous period, well before the Laramide Arc even started, a major normal fault, known as the Dividend Fault, ruptured.
Yeah.
The entire southern half of the Bisbee ore body was violently dropped down. Almost immediately, a massive, thick layer of sedimentary conglomerate, known as the Glance conglomerate, was deposited directly over the top of the downdrop block, burying it completely.
Buried under sedimentary rock.
This sudden, deep burial hermetically sealed and preserved that deep, ancient Jurassic oxidation zone, protecting it from the massive erosional forces that scoured the rest of the continent for the next 100 million years.
It put it in a geological time capsule.
Precisely. And we know for an absolute fact that the enrichment happened before the burial because geologists actually find eroded clasts, rounded pebbles and boulders, of the leached capping and the chalcocite ore incorporated directly within the base layers of the overlying Glance conglomerate itself.
The enriched rock was eroding into the sediment that eventually buried it.
Exactly.
And finally, we have to talk about the absolute, undisputed giant of the Southwest, Morenci, Arizona. The numbers here are just dizzying.
It's massive.
The deposit contains 4.7 gigatons of ore at an average grade of 0.52% copper. That is 4.7 billion metric tons of copper-bearing rock. It is an unfathomable civilization-scale amount of metal. How on earth did one location get so incredibly rich and concentrated?
Morenci is the ultimate testament to the power of tectonic recycling. It benefits massively from a phenomenon known as stair-step enrichment.
Stair-step enrichment.
The entire deposit is bisected by a major structural feature called the Copper Mountain Fault. This fault divides the ore body into a western block and an eastern block. At a crucial point in its geological history, tectonic uplift pushed the western block significantly higher than the eastern block.
Okay, so the western side gets pushed up. That means the water table drops relative to the rock, and the old enrichment blanket is exposed to oxygen again.
Exactly. The mature supergene blanket that had already formed on the western block was lifted high into the vadose zone. The pyrite kicked back in, reoxidized, and furiously leached the copper out of the western blanket.
And where did it go?
Because of the structural tilt in the fault geometry, the highly concentrated acidic copper solution didn't just percolate straight down into the western block. It caught the hydrological gradient and migrated laterally, bleeding directly across the fault zone to enrich the adjacent eastern block, which was sitting at a lower elevation.
So the western mountain basically sacrificed its own copper to feed the eastern mountain.
That's a great way to look at it. The destruction of the Western blanket fed an immense continuous stream of copper into the Eastern Bloc.
Creating a superdeposit.
As a result, on the eastern side of the fault, you have this massive, highly mature, hyper-concentrated chalcocite blanket that is up to 250 meters thick in places. It is a superdeposit built on the cannibalized ruins of the deposit next door.
So what does this all mean for us today? The Porter data paints this incredibly majestic, slow-motion picture of the Earth, carefully refining its resources over millions and millions of years. It feels almost poetic.
It is in its own way.
But I want to abruptly transition to the USGS report on volcanic-associated massive sulfide deposits, because there is a very real, very present-day environmental flip side when all of this complex chemistry suddenly meets the modern surface.
Indeed, and this is where the timeline accelerates terrifyingly.
Yeah.
The USGS paper shifts our focus away from deep geological time and looks squarely at the modern, real-time consequences of exposing these massive, concentrated bodies of sulfide minerals to the atmosphere and our active water cycle.
Okay.
And the crucial thing to understand is this. Whether these sulfide ores are exposed incredibly slowly by natural tectonic uplift and erosion, or whether they are exposed instantaneously by modern, mechanized human mining operations, the fundamental chemical reaction is exactly the same.
It's the exact same pyrite reaction we just talked about.
It is identical. The oxidation of pyrite and other metallic sulfides in the presence of water creates concentrated sulfuric acid, which in turn mobilizes toxic heavy metals. That is the immutable chemistry.
So what's the difference?
The massive difference, however, is the rate at which the reaction occurs.
Right, because when human mining operations blast the rock, crush it up, and run it through a mill, they're taking a solid mountain and turning it into billions of tiny pieces.
Surface area.
They are exposing vastly more surface area to oxygen and water instantaneously, accelerating a reaction that normally takes millions of years into something that happens in a matter of months.
Exponentially accelerating it. And the result of that hyper-accelerated weathering is what environmental scientists and the mining industry call acid mine drainage, or AMD.
AMD.
It is one of the most pervasive, difficult-to-manage environmental liabilities on the planet.
The USGS report features a fascinating diagram called the Ficklin plot. It essentially plots the concentration of dissolved metals against the pH level for various types of mine waters around the world. Where do these VMS deposits that we've been talking about land on this chart?
They plot in the absolute extreme, most dangerous corner of the graph. The field characterized by extreme metal concentrations and extreme acidity.
Why is that?
Because VMS deposits, unlike the heavily dispersed porphyry deposits, are essentially solid, concentrated masses of iron and base metal sulfides. They represent an enormous, highly potent potential source of acid generation.
Like a battery.
They are basically massive batteries of stored chemical energy just waiting for oxygen to close the circuit.
But it's not always the same everywhere.
Right. No, the report stresses that the key variable in whether a site becomes an environmental disaster isn't just the sulfide itself, it's the buffering capacity of the surrounding host rock.
This raises an important question. We talked about limestone acting as a geological antacid earlier. Why are some VMS deposits vastly worse for acid drainage than others? Don't they all produce acid?
They do, but it comes down to that rock chemistry again. Let's look back at the Cyprus type and the Kuroko type VMS deposits we discussed.
The ocean floor versus the island arcs.
Cyprus types, remember, are hosted in ophiolites, mafic submarine volcanics, primarily basalts. Basalts chemically contain a high proportion of minerals that have a reasonably good capacity to neutralize or buffer acid.
They act like the tums.
They aren't as good as limestone, but they help. So while the sulfide in a Cyprus-type deposit generates plenty of acid, the basalt host rock immediately goes to work mitigating it. It buffers the water, keeping the pH from dropping to catastrophic levels.
But the Kuroko types are different.
Very different. Kuroko types, formed in those volcanic island arcs, are hosted in felsic rocks, like rhyolites. Felsic rocks have an extremely high silica content and incredibly low natural buffering capacity.
So they don't fight the acid.
Furthermore, the intense hydrothermal fluids that originally formed the deposit created an alteration halo around the ore body. They essentially baked the surrounding rock, turning it into a zone composed almost entirely of quartz and sericite clay.
Which means what for the acid?
Quartz and sericite offer absolutely zero acid neutralization. So when the pyrite in a Kuroko deposit is exposed to air and water and starts generating intense acid, there is literally nothing in the surrounding rock chemistry to stop it or slow it down. The acid runs pure.
The report also points out that the local surface climate matters immensely in how this environmental threat plays out on the ground. They do a direct comparison between massive sulfide deposits located in Prince William Sound, Alaska, versus deposits in West Shasta, California.
Climate entirely dictates the hydrology of the acid drainage. Prince William Sound in Alaska is a temperate rainforest environment. It receives immense, relentless amounts of rainfall and snowmelt.
So lots of water.
Now, the water draining from those exposed sulfide deposits is definitely acidic, and it certainly carries an elevated load of mobilized metals. However, the sheer, staggering volume of clean, fresh rainwater constantly flushing through the system massively dilutes the acid.
It dilutes
It
it.
acts as a continuous flush, keeping the concentrations relatively low in the downstream watershed.
But West Shasta, California is a totally different beast.
It's a completely different hydrological regime. West Shasta is a semi-arid climate. You have a wet winter season followed by very long, incredibly hot, dry summers.
Like we talked about earlier.
During those intense dry spells, the water flowing through the fractured rock evaporates. As the water leaves, it concentrates the remaining acid and the dissolved metals to an extreme, almost unbelievable degree.
Which leads us directly to the Iron Mountain Mine in California, located right there in the West Shasta district. The USGS text shows a fact here that honestly forced me to reread the paragraph 3 times to make sure I wasn't hallucinating.
It's quite the fact.
This specific site produced the most acidic mine water ever recorded anywhere on Earth.
The analytical numbers from Iron Mountain are genuinely staggering, and they push the boundaries of what we normally consider natural water chemistry. The pH of the water seeping from within the mountain was measured generally at 1.5, which is already highly acidic.
Yeah, 1.5 is bad.
But in specific localized pools within the mine workings, the pH was measured at literally less than negative 1.0.
Okay, stop right there. How is negative pH even mathematically or physically possible? I thought the scale only went from 0 to 14.
It's a common misconception. The pH scale is a logarithmic measurement of the concentration of hydrogen ions in a solution. A pH of 0 means a 1 molar concentration of hydrogen ions.
Oh, okay.
If the concentration of acid gets higher than 1 molar, the logarithm mathematically drops into negative numbers.
So what is negative 1.0 comparable to?
To give you some real-world context, the battery acid in your car has a pH of roughly 0. The water dripping inside Iron Mountain is literally orders of magnitude more corrosive than battery acid. It will actively eat through standard mining equipment, boots, and tools in a matter of hours.
That is terrifying.
And it's not just the acid. Because the water is so incredibly acidic, it dissolves the surrounding rock with frightening efficiency. That dripping mine water contains up to 11% dissolved iron, 2.3% dissolved zinc, and 76% sulfate by weight.
It's practically a liquid mineral.
It is so saturated that as it drips, it actively precipitates bizarre efflorescent metal sulfate salts, bright blue and green minerals like melanterite and chalcanthite that grow like terrifying stalactites in the mine adits.
The colors must be beautiful but deadly.
And unfortunately, that extreme acid also strips out and carries incredibly high, highly toxic levels of trace metals like arsenic, cadmium, lead, and antimony.
The USGS text mentions a concept related to those exact salts called stored acidity, which basically sounds like an environmental time bomb waiting to go off. How does that mechanism work?
This is a massive ongoing concern for environmental management in semi-arid environments like California or the Southwest. During those long, hot summer dry periods, as that highly acidic water slowly evaporates, those highly soluble sulfate salts, the melanterite, precipitate out and form thick, colorful crusts and incrustations all over the rock faces, the mine dumps, and the tailings pile.
Okay, so they turn solid.
Now, while they look like solid rock, what they actually are is solid, crystallized acid. They essentially lock the concentrated acidity in all those toxic heavy metals into a fragile, highly soluble crystal form. They store the acidity on the surface of the landscape.
And then winter comes.
Exactly. When the wet season finally arrives, or when a massive, sudden flash flood rainstorm hits the area, the water washes over these vast fields of crusty salts.
And what happens?
Because they are highly soluble, they dissolve almost instantly. This sudden dissolution releases a massive, highly concentrated, toxic pulse of acid and heavy metals directly into the local creeks and rivers all at once.
It just flushes it all out.
This first flush event can cause catastrophic drops in river pH for miles miles downstream, which can be absolutely devastating to fish populations and aquatic ecosystems.
Which brings us to the final crucial part of our deep dive, finding the ore and managing the fallout. If these VMS deposits are so potentially hazardous, and if they're often buried underground or much smaller than those giant sprawling porphyries, how do geologists even find them in the first place?
Fortunately, the very nature of massive sulfide deposits, the fact that they are essentially solid, unbroken lumps of metallic minerals, makes them stand out incredibly well using modern geophysical techniques.
How so?
Normal rock, like granite or limestone, is an electrical insulator, but a dense concentration of metallic sulfide is highly conductive.
Oh, that makes sense.
Because of this, the USGS report notes that geophysics is the primary tool for discovery here. Geologists use methods like self-potential or SP surveys.
How does a self-potential survey work?
It's fascinating. You are basically measuring the Earth's own battery power. Remember that the top of the sulfide deposit is interacting with oxygenated groundwater, while the deeper part is in anoxic water.
The oxidizing versus reducing environments.
This creates a massive, natural galvanic cell, a battery. The oxidizing ore generates a weak but measurable continuous electrical current in the ground.
Do they just measure it?
By driving electrodes into the soil at the surface, geophysicists can literally map out the shape of the natural electrical field and pinpoint the buried ore body.
That is brilliant. And they use induced polarization too, right?
Yes, induced polarization, or IP, is huge. Instead of passively listening for a current, IP involves actively pumping a known electrical current into the ground to charge up the sulfide minerals, again like a battery, and then shutting the current off and measuring how long it takes for the rock to discharge.
And sulfides hold it longer.
Sulfides hold a charge much longer than barren rock. They also use various electromagnetic or EM surveys where you can essentially fly an instrument suspended from a helicopter over the ground, emit an electromagnetic pulse, and map the electrical conductivity of the buried sulfide lens below.
So the technology to find them is highly advanced. But once we locate a VMS deposit and we decide to mine it, how do we process the ore safely? Because considering all the extreme environmental risk we just talked about, the -1 pH water and the toxic metals, handling this rock seems inherently dangerous. The text mentions the VMS ores are notoriously tricky to process.
They are metallurgically very tricky because of how they formed. Remember those deep sea vents? The metals precipitated out very rapidly in chaotic, turbulent conditions.
So they're all mixed together.
As a result, the different sulfide minerals, the valuable copper chalcopyrite, the valuable zinc sphalerite, and the worthless iron pyrite, are often incredibly fine-grained and intimately intergrown with one another at a microscopic level.
It's hard to separate.
It's not like picking chocolate chips out of a cookie. It's like trying to separate the flour from the sugar after it's baked. To successfully separate the valuable copper and zinc from the worthless acid-generating pyrite, metallurgists have to perform a beneficiation process that involves grinding the raw rock into an incredibly fine, almost talcum-like powder.
And grinding it that fine creates a massive exponential increase in surface area, which means it is going to react with oxygen and water infinitely faster than a solid rock would.
Precisely. That is the core of the challenge. This fine sulfide dust, known as tailings, is phenomenally reactive.
What happens to it?
If it is left exposed to rain, it will generate acid almost immediately. Furthermore, if it dries out completely, it becomes light enough to be windblown, which can physically spread heavy metal contamination, particulate lead and arsenic, across the surrounding local environment.
So, given what we know now, how does the modern mining industry manage this today versus how they used to do it 100 years ago? Because obviously, Iron Mountain is a relic of the past.
The contrast between historical practices and modern engineering is stark, and it's driven entirely by our improved understanding of the geology and chemistry.
How do they used to do it?
Historic legacy mining operations often simply discharge these highly reactive, finely ground tailings into unlined natural depressions, valleys, or shockingly, directly into local rivers and waterways. They left them fully exposed to oxidized groundwater and the atmosphere.
That's just asking for trouble.
That ignorance of the chemistry is exactly what caused the severe, ongoing acid mine drainage problems at legacy sites like Iron Mountain or the old workings in the Rockies.
But today, the regulations and the science demand a totally different approach.
Completely different. Modern operations approach tailings management as a highly sophisticated geotechnical engineering challenge. If tailings must be stored on the surface, they use rigorously engineered tailings impoundments featuring multiple layers of impermeable synthetic linings and compacted clay to absolutely prevent any acidic seepage from reaching the underlying groundwater aquifers.
So they seal it off.
The water covering the tailings is carefully managed to create an anoxic barrier, preventing oxygen from reaching the pyrite.
Keep it underwater, keep it away from the air.
Exactly. But even better than surface storage, many active underground mines today utilize a process called backfilling.
How does that work?
They take the sulfide-rich, acid-generating tailings from the mill, mix them with a specialized cement binder to neutralize them and make them solid, and then pump that thick slurry directly back underground.
Filling the holes they just dug.
They use it to physically fill the empty structural voids, the stopes, where the original ore was blasted out. By entombing the reactive rock deep back underground, encasing it in cement, and keeping it far below the water table and away from surface oxygen, the threat of surface contamination is virtually eliminated.
It really is all about managing the chemistry. It's about keeping the oxygen and the water as far away from the pyrite as humanly possible. And this, ultimately, is where the two massive geological reports we've discussed today seamlessly merge.
They absolutely do.
Understanding the deep, millions of years old geologic history, understanding the slow tectonic uplift, the specific faulting, the precise mineralogy and rock chemistry that the Porter paper details so beautifully, is exactly what allows the geologists and the environmental scientists from the USGS paper to predict exactly how that rock will behave when we dig it up today.
That is the crucial synthesis. If an environmental engineer doesn't deeply understand the primary hypogene mineralogy of the deposit, if they don't map out the presence of neutralizing carbonates versus inert silicates, if they don't know the specific trace elements trapped in the microscopic crystal lattices of the ores, they cannot accurately model or predict the acid-generating potential of the waste rock.
They'd be flying blind.
They can't design the right mitigation strategy. The deep geologic past is the absolute key to environmental mitigation and responsible resource extraction in the present.
Let's bring this all together. The copper that wires our modern world, the literal physical backbone of our entire electrical grid, our renewable energy systems, and the digital devices we hold in our hands, is not just a commodity.
It's definitely not.
It is the final product of subduction zones tearing continents apart, underwater volcanoes erupting in the dark, and tens of millions of years of violent tectonic upheaval. It requires the Earth to perfectly cook the magma, hydraulically fracture cubic miles of rock, bury it under ash, tilt it sideways on massive faults, and run a natural, acid-driven chemical refining process over eons just to make it concentrated enough for human civilization to finally use.
It is a humbling realization, and we must recognize that the act of mining that copper, of harvesting that geological wealth, means taking on the immense, profound responsibility of carefully managing the very same intense acid-generating chemical reactions that created the ore in the first place.
Right.
When we mine, we are forcibly cracking open the Earth's ancient chemical vaults, and we have to handle the potent contents with immense respect for the sheer power of the chemistry involved.
The next time you walk into a room and casually turn on a light switch, or the next time you plug your phone into the wall, take just 1 second to realize what you are actually doing. You are tapping into a resource that is older than the dinosaurs. You are utilizing a metal that was shaped, refined, and hidden by the violent, majestic reshaping of the continents themselves.
And I'll leave you with a final, somewhat provocative thought to mull over long after this deep dive ends. We've spent the last hour discussing how supergene enrichment is just the Earth's natural way of relentlessly leaching, concentrating, and refining metals at the water table over millions of years.
Yeah.
Well, what do you think will happen to our highly refined, metal-rich modern cities, our massive landfills overflowing with electronics, and our sprawling subterranean infrastructure millions of years from now?
Yeah.
When the tectonic plates inevitably shift again, and our buried copper wires, our resting steel beams, and our meticulously engineered cemented tailings ponds are subjected to the deep crushing pressure of the crust and the relentless flow of highly acidic groundwaters, will future geologists far, far down the geologic timeline view the compressed, altered ruins of our human civilization as just another bizarre, hyper-concentrated, massive sulfide deposit waiting to be leached, enriched, and recycled by the next tectonic cycle?
As an amazing thought.